Alright, so for our project, we created a mineral classifier application for mobile devices. My name is Ivan.
My name is Wai.
Yeah, so in terms of for our project, we specifically trained a CNN-based image classifier to be incorporated into a mobile app that facilitates in identifying various different minerals and semi-precious gemstones, with the app being tailored to beginner mineral and gemstone enthusiasts who are interested in locating and identifying these minerals out in the open, as well as a proof of concept for geologists who also plan to use the app in the field with limited computational resources and/or physical access. So for our datasets that we use to train the model is called the Mineral Image 5K dataset, which has mineral images of around 5,000 different mineral types, spanning a total of around 44,000 different unique images. And to keep things simple, we chose 10 classes to train the model based on criteria, which I'll explain later. So, and besides the images, the dataset also conveniently came with a CSV that contained additional information for each image, which included the image dimensions, the type of mineral depicted in the image, and a strong representation of bounding boxes for different objects depicted in each image, which was really useful to us during the data preprocessing step. And speaking of data preprocessing, the operations that we perform can be split into three primary components: data cleaning, selection, and other post-processing tasks. So for data cleaning, we first had to perform a data integrity check on all of the images that were listed in the CSV due to some of the images were found to be missing from the dataset when training. And besides that, we also removed rows that were not planned to be used. For data selection, we chose 10 different mineral classes to train the model, as mentioned earlier, based on the number of unique samples for each class, with higher numbers being preferred, as well as the uniqueness of each mineral class itself, where we didn't want to train the model on minerals that all looked the same. And besides this, we also performed oversampling due to inconsistencies in the class distributions, where some of the minerals like quartz had over 1,000 different images, while the other classes had less than 100. For other operations, we applied image augmentations to every oversampled image, which included horizontal and vertical flips alongside random brightness adjustments. We also leveraged the bounding boxes included in the dataset to crop each image to reduce the amount of miscellaneous objects in each image, if there were any, and applied other image preprocessing effects such as normalization. So for the model that we went with, it was a custom convolutional neural network consisting of two pairs of two consecutive depth-wise convolution layers, each of which was separated by a ReLU and batch norm, where each pair is followed by a max pool layer alongside batch norm and dropout layers, and a final fully connected linear layer at the final fully connected section of linear layers at the end that takes the flattened inputs of the two convolutional layer pairs. And to keep the model size small, we chose relatively small kernel sizes for each convolution layer paired with slightly larger kernel sizes for the pooling layer, so as to reduce the overall dimensionality quickly before flattening and moving into the fully connected layer. And as a result, our fully connected layer had relatively small number of parameters, which altogether yielded a total model weight size of just 697 kilobytes. For the project, we did try to use pruning to further reduce the model size, but we found that after fine-tuning the pruned model, the size of the weights maintained mostly the same, while the accuracy became lower. And here's a broken down visualization of the most relevant parts of the model, with the leftmost figure showing the architecture for the dual depthwise convolutional layers, the middle figure showing the max pool segment that comes after each of the dual depthwise convolution pairs, and the rightmost figure showing the architecture for the fully connected linear layers at the very end of the model.
OF has two main features, capture mode and real-time mode. In capture mode, it process image capture from the take photo function and display the result in the text area. And in real-time mode, the input become the real-time image feed from the camera that will be continuously processed. For the app architecture, this app uses either real-time image or image capture as input, utilizing the camera X library. Then it uses executors to run the machine learning model on the image input. For real-time image mode, it is achieved by using image analyzer extension, binding it to the image feed. And finally, the input is displayed in text format on screen, including classification label, confidence score, and latency. Here is our model performance on 10 mineral class with overall accuracy of 0.75. We got the best precision score of 0.86 with spinel class, and the best recall of 0.9 and the best F1 score of 0.86 with amethyst class. And our app performance is measured on two devices, Samsung S24 and Samsung S10. For latency in capture mode, we got about 75 milliseconds on S24 and about 120 milliseconds on S10. For real-time mode, we got a latency of about 19 milliseconds and 25 milliseconds. Next is the app size at 50.39 megabyte and 51.36 megabyte. And on both devices, we use the same model weight, the size of 697 kilobyte.
Alright, here's a video demonstration of the app that I've tested using some of my mineral samples and other images of minerals. So shown here is a piece of spinel, which is a semi-precious gemstone that was commonly confused with ruby, and so as you can see that the app is able to fairly accurately state the mineral class for both the capture mode and the real-time mode of the app. So here you can see the confidence score is around 80 to 70%. And up next is a chunk of amethyst, where you can see that the app is having no problem in identifying the mineral with very high confidence of almost 100. And here's a chunk of unpolished agate, and you can see that it's also able to accurately identify as the mineral, so around 70 to 80% confidence. And right here is a sample of polished agates, which is the same mineral type as before, and as you can see, it's also able to, the app is also able to properly identify the mineral as the appropriate class, so around 80 to 90% in terms of confidence. Yeah, and here are some of so here is just a sample of aquamarine, which is a type of beryl, and you can see that it's also identifying it pretty accurately with a high confidence. And this is a sample of copper ore, which as you can see, it's also able to identify it for the most part correctly. And finally, here is it's just a sample of a gold ore, and it does misclassify for copper for some cases, but it does eventually correct itself to gold. So you can see that it's right now it's at like 90% confidence for gold. So the app does work. So in terms of the reflection and future work, so when we tested our app on the mineral samples that you've seen just now, we noticed that for some of the classes, particularly quartz and topaz, the model was not able to accurately classify samples that fell under those categories. And upon going through the samples for those classes, we found that although those mineral classes had the biggest amount of unique images, many of the samples depicted in the images were either part of other miscellaneous objects, where, for example, some of the chunks of the mineral were placed in glass bottles, which probably threw off the prediction, or had a very high variability in the samples themselves, where, for example, once again, the quartz samples, they were not all clear quartz, but some of them had different variations of quartz, such as milky quartz and smoky quartz. And this leads us into the potential future work that can be conducted for this project, which primarily entails in creating a dataset using primary sources so as to train the model on a much higher quality dataset, as well as exploring other different model architectures for potentially being able to classify samples with high visual variability. And these are our GitHub links. So we split the model both into the model training projects as well as the actual mobile app itself. So yeah, thank you for listening in.